Nous allons aujourd'hui avoir une conférence avec New York par la magie de Zoom. And I will speak in English. I want to thank especially Ernie Davis for connecting with us at an early time for New York. Professor Davis is a professor of computer science at NYU, New York, and associated with the Courant Institute of Mathematics. And he's a specialist of artificial intelligence as well as natural intelligence, and that is the topic of today's talk. He will tell us about common sense physical reasoning. Can machines have a common sense, a sense of physics, and how does it compare in humans and machines? Last week we talked about intuitions of mathematics, high-level mathematical concepts as well as simple ones such as fractions. Today we will speak about what machines can do in the domain of common sense. So thank you so much, Professor Davis. And well, the floor is yours, and I think we can all hear you.
Thanks very much. It's a great honor to be here, particularly as the guest of Professor Dehaene, whose work I've admired for many years. So I want to talk today about common sense physical reasoning in human beings and in machines. So people and animals interact in many different ways with the physical world, which is immensely complex. And for many applications, computer systems will have to do likewise. And the question is, how is this done? So on the cognitive side, how do people or animals carry out common sense physical reasoning? And then on the AI side, how can you build an AI program which has common sense physical reasoning? And I should say I come from the AI point of view, so that very much informs what I'm going to say. My focus is from the AI point of view. Let me just outline where I'm going. First of all, I'll speak briefly about what I mean by common sense, and then at more length about why common sense physical reasoning is important for various applications. Talk about some of its characteristics that are easily overlooked. Then I'll give some cognitive results, a few experimental results about people's reasoning, which I thought were notable. I'll discuss various approaches that have been suggested and attempted, and then I'll outline the challenges that face us in answering these two questions. So what do I mean by common sense? Well, it's obviously a vague term, and there's no point trying to make it very precise, but three features stand out. One is that it's mostly learned by experience. It's not formally taught in school. It's assumed in school. It's mostly learned young. A child of 7 or so has most of what one considers common sense reasoning. And most critically, it's common. That is to say, we all have it, and we all assume that everybody else has it. So when you're talking to somebody else, you can assume that they know it, and you don't have to explain it. And of course, who exactly is included in we all depends somewhat on the circumstance. And again, it's no need to make that very precise. So why is it important? Well, from the AI point of view, at least, it's important because it's a component of other intelligent tasks, including acting, vision, interpreting what you see, planning, design, language, learning, and at a more sophisticated level, understanding science. So let me just talk about each of those briefly. So that it's a part of acting and planning and vision is obvious. So these two pictures illustrate it. On the one hand, if you think of the term person who's acting, this robot, by cutting the branch on this side, is acting foolishly. On the other hand, you viewing the picture can see what's going on and can predict that if he succeeds in cutting through the branch, he will fall down. And then there's this picture on the right. if you are making these, if you are cutting up these kinds of open sandwiches, you have to do a fair amount of physical reasoning about how the knife is going to interact with the foodstuffs. And again, in viewing the picture, you bring to bear common sense reasoning in understanding what's going on. Seeing that it's a knife, for instance, which just in terms of the image is not all that obvious. Here's a nice example of design from Jacques Carlman's Objet Introuvable from the 60s. This is a design for a picture which will not work very well for obvious reasons. And again, when it's obvious on seeing it that there's a problem here. Common sense reasoning also enters into language use and comprehension when that touches on physical situations. So here's a problem in translating a sentence from French to English, and I will ask Stanislas to read the French because you don't want to hear me pronounce French. Stanislas? Oh well. Anyway, here's the French sentence, which I will not attempt to read. And the question is ça-vous correctly translated as his view or her view? Pronouns in French agree in gender with this object possessed, but in English with the possessor. So it's obvious in this situation, Henry is very tall and he's sitting in front of Mary, so it must be her view of the stage was blocked, but Google Translate gets it wrong. And the only way to get it right is by considering the physical situation here. All right, another example. This is a quote from a biology textbook. Subpopulations of a species can be isolated if the water level of a lake falls, dividing it into two lakes. So here we have, you can understand how this works in terms of your understanding of how water interacts with solid objects. Another example, this is from Michael Faraday's lectures for children from 1848, The Natural History of a Candle. He describes this experiment where you have iron filings being heated and water boiling, and the iron reacts with the water to create rust and hydrogen. So this is a way of getting hydrogen. And understanding this involves not just understanding the chemical reaction, but also this whole apparatus. And this is, this is large amounts of understanding of heating and gas movement and bubbling through liquids and so on. Okay, let me talk about a few of the characteristics of common sense physics. They cover a wide range of phenomenon. They depend on complex spatial properties and relationships. They are, common sense reasoning is robust under partial knowledge, and it can handle a wide range of scale. So let me talk about each of those. Phenomena. You have many different kinds of material. So just in the context of cooking, let's say, you have hard solids like utensils and certain kinds of foods like potatoes. You have soft solids like cheese and fresh parsley. And these are soft in different ways, depending on the type of cheese. And cheese is in any case different from parsley. You have powders such as flour and salt. You have liquids such as milk. You have light, which is important. You have fire, which is also important. Pardon me. There are different kinds of processes. So again, just in the cooking domain, you have cutting, warming, chilling, mixing, dissolving, kneading, carrying, breaking eggs. Just for cutting, the number of different tools that one has in one's household purely for cutting, for slicing objects up or for shredding them, separating them into pieces somehow is remarkably large. There are knives, there's scissors, shears, wire cutters, files, lawnmowers, cheese graters. And you understand how to use all of these and how they will work, and even how they will work under anomalous situations. You understand what will happen, let's say, if you try to use a knife to slice a piece of wood, or if you try to use a lawnmower to cut your hair, and so on. And then a large part of what one knows about the physical world has to do is biophysics, so to speak. It has to do with what your own body and what other people's bodies can do in terms of motion and manipulation and perception and biological processes. There's a lot of knowledge of this kind. It obviously interacts with reasoning about non-biological things, because one manipulates or is impacted by these external objects. And so this all has to be understood. Complex spatial properties and relations. These shapes and the spatial structures of common objects can be remarkably complex. So here is, on the left, is a cheese grater. And so you have the overall structure, this sort of frustum of a pyramid with the handle to hold it in place. And then you have a smaller repeated structure of holes. And each of these holes has this little blade with a cup that comes out to slice the cheese. And so this is a rather common, and of course you have different types of holes on the different sides of the device. So this is a rather complex shape to reason about, but we're familiar with it. And if you think about the process of grating, let us say, a cheddar cheese against this side of the grater, and you think about the shape that the piece of cheese gradually deforms into, you have a reasonably complicated geometric problem going on there. Here you have a string bag, and the thing about a string bag is that it has a fixed structure. An important one. So it can be open, so you can put things like peppers into it, and it has holes, but the holes are small enough that the peppers don't fall through, whereas a pea, let us say, would fall through, and an elephant can't be put in the bag. And it has this network structure, and it's made of string, so it's very much deformable. If it's empty, you can fold it up and put it in a wallet. So you understand the whole, as they say, configuration space which this object can attain, which is complex. And you understand the relationship between its spatial structure and its physical properties and its uses, which is also complex. Partial knowledge. A great thing, an important feature of common sense reasoning is that it deals robustly in situations where your knowledge of the physical situation is incomplete, maybe extremely incomplete, for a variety of reasons. First of all, perception is limited. You only see the front of solid objects at the best of times. Unless they're transparent, of opaque objects, you only see the front. And you may see only part of it may be occluded, and so on. The situation may be described in language. So I gave you the sentence before about the two people at the theater. I didn't specify how tall Henry is, or how much in front they are sitting, or where they are sitting in the theater. So you have only a very partial description, and yet you can do the reasoning you need. Some of the information may be inferred from seeing how things behave. You may need to reason generically. You want to be able to reason, let's say, that your string bag will not just hold this pepper or that pepper, but it will hold any pepper. You may be in the middle of designing the object. You have the object partially thought out, and you want to, as part of the design, you want to make sure that you're on the right track without fully specifying yet how exactly it's constructed. There may be unknown external events. You want the bridge to continue to stand despite unknown traffic and weather events and so on. And in many situations, the physical processes are only partially understood. You don't have a full physical theory of what's going on. So, for instance, if you are frying an egg, you probably don't know, I certainly don't know, the physical chemistry that's involved in turning a raw egg into a fried egg. But that doesn't mean that frying an egg takes place in some kind of physics-free zone where I just I've learned the standard process by rote. No, I know a great deal about it and I can use that. So I know, for instance, that if I pick up the pan, the egg will stay inside, and that as the egg cooks, it becomes easier to pick it up, and that the more raw egg I start out with, the more fried egg I will end up with, and so on. There's a great deal of physical knowledge without having a full physical theory. Or another example, you take an iPhone and you chop it in half with an axe. So you can infer that it's not going to work anymore, despite not having a very clear idea of what the internals of the iPhone are, or how chopping the iPhone in half with an axe will affect those internals. Finally, you have to reason across a wide range of scales. So an event which lasts, let us say, a tenth of a second, if it's important enough, take a bullet, say, that may affect your life for your remaining 70 odd years. And that's a ratio of 10 to the ninth. That also comes up in psychological reasoning, by the way. A poorly chosen response to, a poorly chosen statement, if it's poorly chosen enough and the situation is delicate enough, may impact the rest of your life. Or in the spatial domain, if you drive from Paris to Delhi, which is 6,000 kilometers, that involves a variety of actions, some of which are very small. So it involves many times shifting the steering wheel by centimeters. And that's a ratio of 6 times 10 to the 8th. And then, of course, once you get into scientific reasoning, these ratios become much larger. You get ratios of 10 to the 57th and 10 to the 200th and so on. Okay, so that's why it's important. Let me talk about a few experimental results in human physical reasoning that I've found intriguing and impressive. So first, physical reasoning in infants. Secondly, a number of studies of situations where people make erroneous predictions, and a revision of that. And then talk somewhat about studies of visualization as a process. So there's a literature of very ingenious studies of how much pre-verbal infants understand. And you might have thought that that's impossible to test. I would have thought so, but this is the general method that's used, or one of the general methods that's used. So you have an infant, and it's looking at some situation that you've set up. And it turns out that if what they see surprises them, then they will stare for longer than if it doesn't surprise them. If it's usual, they don't look at it very long, but if it's unusual, then they will stare at it longer. And this apparently is a robust and replicable effect. And so in particular, if you show them a situation that seems to violate a basic physical law, it will surprise them and they will stare. And so scientists like René Bayerjan at University of Illinois Champaign have done experiments like this. They show they demonstrate that infants from as young as 2.5 months to 5 months are actually surprised when an object is hidden in one place and then reappears in a different place, or when when an object goes behind a screen and you lift the screen and the object is no longer there, or when you show that there's an obstacle and you put a screen in front of it, then the object seemingly goes through the obstacle, and so on. So infants of this young age can be shown to have some basic understanding of the properties of objects. They move continuously, they persist, and so on. There are a number of experiments which show situations where naive subjects make erroneous predictions. So do more sophisticated subjects if they're not on their guard, like physics majors, college students who are majoring in physics. So here's the problem. The diagram shows a thin, curved metal tube. You are looking down onto the tube. You place a ball at the end of the tube here, and you shoot it fast through the tube. And the problem is to draw the path that the ball follows when it comes out of the tube. Okay, so you can think about that for a second. The answer is that it goes straight in the direction. Right? This is Newton's law. It does like this, right? Newton's law is that once it has no forces acting on it, it travels in a straight line. But many subjects predict that it has sort of a circular momentum that persists for a while, so it continues to travel on a curved path which gradually straightens out. Another experiment had to do with this. You have a swinging pendulum, and you cut the string at some point in its motion. And the subjects were asked to draw the trajectory of the bob after the string was cut. And very few subjects got this right. So you can see the various results here. Nobody gets, none of these are right in all 4 situations. 25% of the people, the top row here is more or less correct. So 25% of the people get it actually right. The remaining 75% get it wrong in one way or another. But recently there was a follow-up to that experiment, which was remarkable. Which is that this is task dependent. It's very true, and they replicated the result, that people are terrible at drawing the path that the bob will follow. On the other hand, if you ask them to place a bucket in a position which will catch the bob, then they do quite well. They're much better than they would if they draw, much better than would be predicted from drawing the path. So this indicates that they are using different reasoning mechanisms in these 2 situations. And, it's a matter of study now, what mechanisms are being used and how the cognitive reasoning mechanism chooses the process to use. As a purely anecdotal illustration of this, but one I'm rather fond of. This is from an article by Rebecca Lawson, a psychologist. She tells a story that she goes scuba diving, and they had left their weight belts on a different boat, and she offered to go fetch them. So she swam over there, took the 3 weight belts, started to swim back, and of course sank like a rock to the bottom of the harbor. So luckily she was able to, otherwise we wouldn't have the article, she was able to drop 2 of the weight belts. But she was shocked that she had made the mistake. After all, she was an experienced scuba diver. She knows how buoyancy works in water. And this was a potentially fatal error. There's some interesting studies of how people use visualization in reasoning. So these are 3 experiments which were done by Mary Hagerty about 20 years ago. The first is a gear rotating problem. So people are shown this situation here with the 2 gears, and they're asked whether the bump on the knob on the left gear will fit into the groove on the right gear if they're rotated inward. This is rotated clockwise, and that's rotated counterclockwise. And what they report and what you can measure in various ways is that they actually run a mental movie of the 2 gears rotating and see whether it fits properly. A second problem had to do with a pulley system. If you pull, you have this system of pulleys, and if you pull on the rope here, the question is, which direction is the lowest pulley moving in? Is it turning clockwise or is it turning counterclockwise? And here again, people visualize, but they don't visualize the whole system of 3 pulleys and 2 ropes moving in a continuous movie, in a unified movie. They visualize pieces and they carry over inferences from one piece to another. Third problem, the diagram shows 2 glasses of water. So the glasses are the same height, and they're filled to the same water level, but one is wider than the other. And the question is, if they're tilted, do they pour out at the same or at the different angles? And if they're tilted at the same rate, which will pour first, or do they pour at the same time? And if you just ask people this question, they generally get it wrong. But if you instruct them to imagine it, then to visualize it, then they get it right, to a large extent. And so this is a process of visualization. Again, this is evidence of 2 mechanisms: a poor mechanism, a less accurate mechanism that's being invoked when they are not visualizing, and a more accurate one that's being invoked when they are visualizing. And the visualization is a conscious process that they can deliberately invoke. Okay, so this is a different kind of visualization problem. Subjects were shown a video of this blue ball moving. So this is shown statically here, but in fact, they were shown a video of it moving along this path. And at each stage, they were asked, will it reach the red region first or the green region first? Various experiments were done. One is they were asked to make their prediction as it went along. Another one is they were shown the trajectory for a certain length of time, and then the vision stopped and they were asked to do it. In the latter situation, the time that they took in predicting it was pretty much proportional to the actual time that it would take. So if they started it, if the video was stopped here, then they would predict that it would go something like this, reach the red region first, and it would take the time proportional to their reasoning would take a time proportional to the time that it would actually require. If the video were stopped earlier, let's say here, then they would trace out the trajectory over a longer path, and it becomes noisier and less accurate, but it also takes longer, and the length of time that it takes is proportional to the physical length of time. On the other hand, there are situations, pardon me, where they can come up with the answer immediately. So in this situation, if you ask them, will it reach the red ball area first or the green area first, they can immediately answer that it reaches the red region first without any need to visualize, because it can't reach the green region because of the, it's inside this container. Okay. I next want to discuss a number of the approaches to to common sense physical reasoning, which have been proposed as mechanisms in common sense psychology and implemented to some extent or proposed in artificial intelligence. So I'll talk about, first of all, physics engines, otherwise known as simulation, about symbolic reasoning, and then about machine learning or pattern learning of three kinds: reinforcement learning, deep learning, and language models. So a popular theory, a popular approach is simulation. So the idea is you have in your head, in your internal mechanism, a physics engine, which is it's like the kind of video games physics engines that power the behavior of more or less realistic video games, and that this is running in your head. This allows you to do the physical reasoning. And these physics engines work, broadly speaking, as follows. You know the state of the world at some starting time, and then you use the laws of physics to predict how the world will change over a small time period, typically a fraction of a second, and you compute the next state, and you iterate, keep doing. So this is the general architecture of a physics engine. And by doing this, you can generate a mental movie of what's going to occur, one state after another in a series of discrete states at short time intervals. There's also a probabilistic Monte Carlo version, in which either the starting state has a probability distribution, or the laws of physics are probabilistic, or both. And you run multiple situations, making random choices according to this distribution, and you do some kind of statistics over the outcome. And this is extensively used in computer software. In fact, these were the very first programs that were run on electronic computers, the ENIAC and so on, back in the 1940s. Many of them were probabilistic simulations for the atom bomb and other applications. And this has been proposed as a mechanism in cognitive theory. There are two versions, and this is an important distinction which is often overlooked. There are two versions of the cognitive theory. One is that you create a mental movie that you can, so to speak, view in your mind's eye. And the results on the gear and the pulleys and the containers of water of Mary Haggerty that I mentioned earlier correspond to that. Subjects report visualizing this, seeing these objects move around. There are also a collection of experiments where the results, the outcomes, seem to correspond to the use of a physics engine, or argued to correspond to the physics engine, but it's quite clear that there's no mental movie that can be introspected on. So for instance, if you see a tower of blocks, an unstable tower of blocks, and it falls over, then you can predict where it will fall to some degree of accuracy. And it's been argued that this is done by using a physics engine, but you cannot visualize at all realistically a tower of 8 blocks falling with all the 8 blocks interacting. Okay, so what's good about the simulation theory? Well, for one thing, it's very general. It applies to essentially any physical situation. It can be applied. It's exceptionally well understood. The mathematics goes back to Euler, Lagrange, Laplace in the 1700s. The computer implementations, as I mentioned, go back to the 1940s. There's lots of powerful mathematics, lots of powerful software, both for computing scientific computing to high degrees of accuracy, and for video games at actual that has to be done in real time and has to be good enough that it's visually convincing. And there's some experimental evidence. Well, there's a lot of articles. There's some of experimental evidence of various kinds, and I should say some of it is more cogent than other. But there are many experiments. There's large literature at this point supporting this theory. What's the problem with the simulation theory? Well, for one thing, it needs a complete specification of the starting state, or some kind of well-defined probabilistic distribution over the starting state. And as I discussed earlier, you often have incomplete information where this don't have. It requires a physical theory which can be stated as a differential or difference equation, differential equation or a difference equation. And again, you don't always have this. And thirdly, it's fundamentally geared toward prediction, and it's only indirectly applicable to other reasoning tasks. Other weaknesses. Physics engine, it's easy to say you have a physics engine, but they are in fact hard to construct. So as a sort of curious example, video games often have doors because the characters have to get from one area to another and they have to be blocked for a while, but they almost always have magical doors. They click on them and the door opens. Very few video games have a physics for doors, and that's because it's quite surprisingly difficult to build a physics engine for a door, within the constraints of a video game. In scientific computing, if you're doing scientific computing of any kind, you build these models, but it requires immense expertise and very considerable labor generally. It's not by any means a cookbook thing to do. And in particular in robotics, one application of simulations that's been studied a great deal is simulations for robots, because letting a robot loose, you don't want to let a robot loose in the actual world until you're sure that it works well, because robots are expensive objects, and if they don't do the right thing, they are liable to break or to break something else. And this turns out to be exceptionally hard. It is so hard that it has acquired a name. It is called the reality gap in robotics. And the experience is you have your simulator and you build it up as well as you can, both the simulator of the robot and the simulator of the world, and you test it. And then you try to apply what you've learned to your actual physical robot in the actual physical world. And it's as if you had to start from scratch. You have learned something useful, but you have a long way to go before you can apply it, before the robot will work in the actual world. In scientific computing, you also need various kinds of further expertise. You need expertise to choose the appropriate model, to formulate the problem, and to interpret the output. More weaknesses of simulation theory: you need unnecessary precision is demanded in the input and produced in the output. So here's a situation where you have a cyclist, he has a water bottle. The water bottle is half full of water. He's driving on a bumpy road. So if you want to simulate what happens with the water, well, it's going to slosh up and down because he's riding it on a bumpy road. And the sloshings will be very complicated. But all that simulation is completely pointless. All you want to do to infer is that at the end of the trip, the water will still be in the bottle. And so you are if you do this via simulation, you're putting in an immense amount of effort for a very simple conclusion. Another approach to common sense physical reasoning is what's called qualitative reasoning. This was extensively studied in the 80s, still somewhat an area of research. So you characterize the state of a system in terms of one-dimensional parameters, and you have a collection. You characterize your dynamic theory in terms of relationship between the signs of their change. So you have rules like that: if X goes up, then Y goes down. And this will work well enough sometimes for systems which have only a small number of degrees of freedom. So a swinging pendulum has only 1 degree of pendulum that's swinging in the plane has only 1 degree of freedom. You have a chain of gears, then that has as a system of as an overall system that has only 1 degree of freedom. And it's had a number of successful practical applications, but it doesn't work well for geometry, and it also has other limitations. There are knowledge-based methods such as logical analysis. This is what my own technical research has been focused on for most of my research career. So you have rules which you can state if you want in a logical-like language, that every object occupies a place which is feasible for that object. This is a simple description for a rigid solid object and a complicated description for a string mag, let's say. You have the rule that any two objects are spatially disjoint, stated this: if you have two objects, P and Q, and P is not equal to Q and T is a time, then the place of P at time T is disjoint from the place of Q at time T. You have a rule that an object moves continuously. H places a function from an object to a history, and this has to be a continuous history, and so on. So you have put together a collection of these rules, and you do inference over these rules. So for the water bottle problem, you would state it as follows: the bottle and the object and the cap are rigid objects, and the water is some kind of stuff. And at the starting time TA, the union of the place of the bottle and the cap are a closed container for the water, and the bottle is sealed. The cap and the bottle are sealed from TA to TB, and you want to infer that the bottle union cap at time TB is still a closed container for the water. And I had a student actually last year who put together a system which could do these kinds of inference over simple examples. The strength of the symbolic approach is, first of all, it works very well with incomplete information and with incomplete physical theories. That's the nice thing about formal logic, is it's really good at expressing certain kinds of incomplete information. It isn't inherently geared toward prediction, unlike physics engine. It can incorporate non-physical information, a drawback of simulation that I didn't mention, and it deals elegantly with a range of scales. But it hasn't been turned into a practical reasoning system. It's extremely hard to formulate theories that are adequate. You need a degree of logical precision to get these right, which is extremely fussy and relies on making very fiddly distinctions and fussy definitions and so on. It's hard to be you want to have some confidence that you can't make absurd inference, and it's impossible to be sure of that, and it's hard to be confident of it. There's currently no inference engines exist that are adequate to the kind of reasonings that would arise in even fairly simple problems. Very few practical applications have been developed so far, and one can certainly debate how plausible it is as a cognitive theory. All right, so now we come to machine learning, which is by far the dominant theory approach to AI these days. And this is of three categories. I have 15 minutes left. I'll assume I have 15 minutes left. There's reinforcement learning, deep learning, and large language learning. And of course, some form of learning theory has to be right, because common sense physical knowledge is learned by babies and by children. And if it isn't learned, then it's innate. And if it was innate, then it was learned by evolution, which is a slow process, slow and painful process of learning things. Okay, so reinforcement learning. The idea here is that a creature or a robot or a simulated robot learns by trial and error what actions work in order to achieve specified goals in a given situation. So as a cognitive theory, this was more or less the theory of behaviorism promoted by B.F. Skinner, which was dominant in the 30s and 40s and has become much less popular since. So it's had some practical successes in some forms of AI. So in robotics, it's been used with some degree of success, and it's a major component in current games playing programs. It's limited as a physical theory. It only learns the relation of actions to goals, and it doesn't generally learn a theory of the domain. And it's very limited as a cognitive theory. Behaviorism is not considered a good cognitive theory anymore. There is deep learning. Deep learning is it's a very general model of learning to carry out intelligent tasks. I'm not going to go into the technical details. It's trained from data corpora, which range from large to enormous. It has a very remote similarity to the way neurons work in the brain. It can be shown that to some extent, it succeeds in extracting abstract features of the situation. That's a matter of study. And above all, it's been enormous. It's hard to exaggerate the success that it has had in artificial intelligence. So deep learning of almost every practical application of AI in the last decade has had a major component or has been almost entirely, depending on the situation, of deep learning. So in vision and natural language, deep learning methods of various kinds are entirely dominant. In games, playing, and robotics, they are combined with deep learning is combined with reinforcement learning. It's still very important. Limitations. It's hard to incorporate domain knowledge. We know at this point a lot about language. We know a lot about physics, and so on. What we know a lot about a lot of domains. In almost all cases, almost all of that knowledge has to be thrown out if one is going to develop a deep learning system. The deep learning system works from the data, and it's very hard to build in what centuries of scientists or lay people have learned about a domain. It often focuses on the wrong features. So for instance, in computer vision, it will often focus on, just prefer to characterize things in terms of their texture rather than their shape, which is more important to people. So if you show a picture, let us say, of a cat which has elephant skin, it will characterize it as an elephant rather than as a cat, whereas a person will say it's a cat, it's a strange cat. It often fails to generalize. So if you train a self-driving car in one city, it may not work in another city. This is one of the things that has slowed down the development of self-driving cars. It is in general an opaque system. You cannot explain how it came up with its results, and therefore you cannot debug the system when it gives wrong results. All you can do is train it some more or change the architecture and retrain. So how does it work as applied to physical reasoning? So it's had important successes in very specific scientific problems. So the great success of AI applied to science problems was a year or so ago was AlphaFold, which made major progress on the problem of protein folding. This was a highly specialized, mostly deep learning system. I said it was applied to robotics, which it is, but if you try to do it purely by deep learning, it doesn't work well. And so far, it's had little success applied to common sense physical reasoning, there's not much reason to think that it finds the right generalization or the right abstract categories. Okay, now finally, there are the large language models, which I trust you have heard of because they have gotten immense amounts of publicity in the last, increasingly over the last couple of years, and particularly over the last couple of months. So GPT-3 got huge amounts of publicity from the press, and then Chat GPT-3, which was released just last November, has gotten immense amounts of publicity. So what are these? These are deep learning models. They're developed specifically for language, and they're trained on huge corpora of texts, hundreds of billions of words, on a particular task, which is to predict the next word. You give them a starting text, they predict the next word, and then given that, they predict the word after that, and given that, they predict the word after that, and so on. They predict word by word. So the output has been extensively reported, is often breathtakingly impressive. They can answer questions they can answer very difficult questions in some cases. They can produce essays of very high quality. ChatGPT-3 can produce poetry that rhymes, not very interesting, but on any topic that you choose to specify, and it does more or less rhyme. On the other hand, the output is sometimes way off base, even on very simple problems. I'll give a couple of examples, sometimes hilariously so. It is subject to hallucinations. If when it doesn't know the answer, it invents things because the things sound good. They don't have good sense of truth or reasonableness. They just know what text sounds like the text that they read. So a well-known description by Tim Nitke-Brew and Emily Bender and a couple of other authors is they're stochastic parrots. They parrot what they've read in a random way, but they don't really understand what's going on. And common sense reasoning, particularly spatial and physical reasoning, is not their strong point. It's a weak point. They don't have any inherent model of space or of time. And looking at text is not a good way to learn about space because language is very strange in how it describes space. So here's a classic example. The trophy didn't fit in the suitcase because it was too small. The question is, what does it refer to? So this is an example developed by Hector Levesque. This is in a paper that he wrote with me and Leora Morgenstern called the Winograd Schema Challenge. And ChatGPT, as of a couple of days ago, got the answer wrong. So the answer was the trophy didn't fit in the suitcase because it was too small. It was the trophy is the object that's too small to fit in the suitcase. However, it's not clear. It goes on to make some irrelevant comments, but it doesn't have a good sense of the spatial and physical relations, so it makes the wrong prediction. Going back to frying an egg, this is an experiment that somebody else tried. I'm frying an egg, but when I flip the egg, it used too much force. What happens? And this is ChatGPT. ChatGPT gave what seems like a reasonable answer. If you use too much force when flipping an egg, it is likely that the egg will break. When you fry an egg, the goal is to carefully flip the egg so it cooks evenly on both sides without breaking. So far, so good. But then when you probe it, it turns out not so good. So he went on to ask which part of the egg is breaking. And the answer was when you fry an egg, the white and the yolk are both held together by the eggshell. And if you use too much force while flipping the eggshell can crack and break, which can cause the white yolk to spill out. So despite the initial success, ChatGPT-3 does not really understand what's going on when you're frying an egg. Okay, so those are the approaches. They each have their strengths. None of them seems to be a complete solution. So overall, I think it's safe to say that there are multiple cognitive processes of various kinds. There are strategies that are for manipulation that are simply learned and part of your muscle memory, so-called. There, under some circumstances, you use visualization. Certainly, use the explicit visualization. Perhaps there is a non-introspectable form of visualization also. In some cases, you can simply look at a scene and perceive what is going to happen. In some cases, no doubt, you learn from a long series of seeing the world. Use corpus-based learning in some manner similar to how deep learning learns vision and so on. No doubt, some of what you learn is based on language, and you learn it through language. I didn't talk about analogy, but analogy would seem to be an important aspect of common sense reasoning, and generally in physical reasoning in particular. And you are, I think, able to do some amount of there's every reason to think you can do some amount of abstract reasoning. You can abstract the physical situation and use that to reason. And these are all combined. But sad to say, we don't really have adequate theories of any of these. We don't know how to integrate them. So it's been proposed that these problems can be solved by using learning technology in a multimodal situation. That is to say, you have both speech and a physical situation and perception. This is, after all, how babies learn, and people and animals. And my feeling is that, at least with the current technology for learning, this will probably advance things somewhat, but it's not likely to give a complete solution for the reasons that I described earlier. And I want to end with a phenomenon that I find very strange, and I think might give some leverage on the problem if we could figure it out, which is people's use of diagrams. And in particular, there is this odd fact that diagrams often have only a very vague qualitative resemblance to the actual situation, and yet can be extremely useful in helping people understand. All right, so this is a diagram from the Feynman Lectures on Physics, a great physics textbook, in which he's describing the behavior of a gas inside a piston. All right, so his description of his diagram shows the gas as, I forget how many these are, 13 or so dots with arrows on them in a box. And somehow this is supposed to give you, this student, an intuition for the behavior of 6 times 10 to the 23rd gas molecules moving at the speed of sound in 3 dimensions. And it somehow does. Another example is, this is an illustration from the article on redshift and blueshift in Wikipedia. So this illustrates that when the star is moving away from the person, the light is redshifted, whereas if moving toward the observer, the light is blue shifted. And again, the relationship between this situation, and particularly the scales here, the distance from the star to the person is shown as being 4 wavelengths, whereas it's more like, I think, 10 to the 200th wavelengths in some cases. And it's a static picture where motion is represented by this ridiculous green arrow. And yet again, it gives people it helps develop people's intuition of how it's going on. And I have the sense that if we could understand what was going on here, that would that would tell us something important. But I don't know how to do it. So that concludes my talk. Thank you very much. And I'm happy to discuss this further.